Welcome back to the deep dive. Today, we're getting into something really core to computer science. A building block you pretty much can't avoid if you're dealing with data.
That's right.
We're talking binary trees,
Yeah,
and we're drawing heavily from Hello Algo, section 7.1 for this one. Our plan, really unpack what these trees are, get the language right, how they work, why they matter, aiming for that deep understanding that, actually sticks.
absolutely. And understanding these core structures, like binary trees, is just crucial. They're like the fundamental grammar of how you organize information efficiently in software. Getting this down is so valuable.
Okay, let's unpack this then. So first principles, what is a binary tree? The source says it's a nonlinear data structure.
Right, nonlinear. That's the key thing to grasp first. Think about arrays
Right.
or linked lists. Data comes one after another in a line, right?
Yeah, sequential.
Exactly.
Hmm.
But binary trees, they branch out. They're perfect for showing relationships where things are, above or below others' hierarchies, like a family tree or maybe folders on your computer.
Oh, okay. Like parent-child relationship.
Precisely. And they also naturally fit that divide and conquer idea. You hit a point, and you can go one of two ways, splitting the problem.
Got it. And the basic unit, like with linked lists, is the node.
Yep, the node. And according to the source, each node holds some value, the actual data. And then crucially, it has space for two references, or pointers. One for a potential left child node, and one for a right child node.
So these pointers are what connect everything up.
They are the connections. They define the whole structure. A node points to another. It's the parent, the ones it points to. Those are its children specifically, left child, right child.
Mm-hmm.
And this leads to the idea of subtrees. If you take any node except the ones right at the bottom,
The leaves.
right, the leaves, any other node, everything underneath its left child forms the left subtree, and everything under the right child forms the right subtree. So each node is kind of like the root of its own little mini-tree, unless it's a leaf.
Okay, that makes sense. Structure comes from nodes and pointers. But to talk about it, we need the right words. There's specific terminology here, isn't there?
Oh yeah, nailing down the vocabulary is key.
All right. So figure 7.2 in the source lays some of this out, starting at the very top. The root node,
The root, that's the origin, the single node with no parent above it.
and then all the way at the other end, the bottom bits are the leaf nodes.
Yep, the leaves, they're the endpoints. No children. Their left and right pointers just point to, well, nothing, null, none.
Okay, and the lines connecting them, those are edges.
Edges, exactly. They visually show those pointer connections between a parent and a child.
Right. Then there's the idea of level, how deep a node is.
Mm-hmm. Usually the root is level 1, though sometimes you see level 0 used. Then its children are level 2, their children level 3, and so on. It just increases as you go down.
Simple enough. And the degree of a node,
That's just how many children it actually has. In a binary tree, it's always 0, 1, or 2. 0 for leaf, obviously.
okay, 0, 1, or 2. Got it.
Now, things get maybe a little more nuanced with terms about distance or size. These definitions can sometimes vary a bit, so it pays to be precise.
Ah, okay. Like what?
Well, first, the height of the entire binary tree. Generally, that's the number of edges on the longest possible path from the root node down to the leaf node that's furthest away.
Longest path, count the edges. Okay.
Then there's the depth of a specific node. This is also about edges, but it's the count from the root down to that particular node. So the root itself is at depth 0, its children at depth 1, and so on.
Right, root is depth 0, level 1 sometimes. Depends on the convention.
Exactly. And then one more. The height of a node. This one looks downwards. It's the number of edges on the longest path from that node down to the furthest leaf in the subtree below it.
Oh, okay. So leaf node has height 0.
Precisely. It has no path downwards.
Gotcha.
And here's that really important tip we mentioned. You really need to watch out for how height and depth are defined wherever you encounter them.
Right, the edge counting versus node counting thing.
Yeah. Sometimes people count the nodes along the path instead of the edges. If they do that, all the values will be one higher. It's a super common point of confusion, so always just double check the context.
Yeah.
See how they're defining it.
Good heads up. Okay, so we know the parts, the words. But how do you actually, build one or change it? You said it's like linked lists about the pointers.
Fundamentally, yes. It's all pointer manipulation.
So to start, you'd, what? Make the nodes first.
Pretty much.
Yeah.
You create the individual nodes, put the values in them, set their initial child pointers to null or nothing. Then you go back and connect them. You tell the root node, okay, this is your left child. That is your right child. Then you tell those children who their children are and so on. You build a web of connections.
Step by step. And adding or removing nodes, still pointers.
Still pointers. If you want to insert a node, you typically find the place it should go, adjust the parent's pointer to point to your new node, and then make the new node's pointers link back into the structure, maybe pointing to what the parent used to point to. And removing is similar, conceptually. You might make the parent of the node you're removing just bypass it, pointing directly to one of the removed node's children instead.
Sounds simple enough, but I sense a but coming.
Yeah, there's a pretty big but. While the mechanics are just changing pointers, doing this can really mess with the logical structure of the tree.
How so?
Well, first, when you remove a node, unless you do some careful rearranging, you usually lose everything below it too. Its entire subtree just gets detached.
Oh, right. That could be a lot of data.
It could. And second, just sticking a node in somewhere or yanking one out might completely unbalance the tree, which, as we'll see, really affects performance. So often, meaningful insertions or deletions aren't just one pointer change. They might involve a whole sequence of adjustments, maybe even restructuring parts of the tree to keep it in a good shape.
Okay, so the shape is really important. And you mentioned not all binary trees have the same shape. The source highlights some key types.
It does. These are common patterns you'll see, representing different structural properties, based on figures 7-4 through 7-7 in the source.
First up, the perfect binary tree. Sounds ideal.
It kind of is visually. Think perfectly symmetrical. Every single level is packed full of nodes, no gaps. And importantly, every node that isn't a leaf has exactly 2 children. All the leaves end up at the same depth.
Very neat.
And it has this neat math property. If a perfect binary tree has height h, the total number of nodes is exactly 2 to the power of h plus 1, then subtract 1. It's this clean exponential growth. The source likens it to, like, cell division.
Cool. Oh, and there is that naming tip?
Yes. Good reminder. The source notes that sometimes, particularly it mentions in the Chinese programming community, the term full binary tree is actually used to mean this perfect structure we just described. So another potential point of confusion to watch for.
Okay, perfect means all levels full, all non-leaves have 2 kids. Got it.
Next is the complete binary tree. This one's almost perfect.
Almost.
Yeah. Every level, except maybe the very last bottom level, has to be completely full. And if that last level isn't full, the nodes it does have must be filled in strictly from left to right with no gaps.
So it's full from the top down and the bottom level fills left to right.
Exactly. And think about it. A perfect binary tree is also a complete binary tree, right? Because its bottom level is full. And it satisfies the left to right rule trivially.
Yeah, okay. Perfect is a special case of complete. Makes sense. What about the full binary tree then, using the source's main definition?
Right, separating this from that naming convention we mentioned earlier. According to this definition from Hello Algo, a full binary tree is one where every node either has exactly 0 children, it's a leaf, or it has exactly 2 children.
So no nodes with just 1 child allowed, except maybe the root if the tree only has 1 node.
Well, yeah, technically a single node is a full tree, but for any node that's not a leaf, it must have 2 children. It doesn't have the requirement that all leaves be at the same depth like a perfect tree does.
Okay, slightly different constraint. Perfect is stricter. Full just means nodes have 0 or 2 kids.
Correct. And finally, a really important one for performance. The balanced binary tree.
This sounds crucial.
It is. The definition is, for every single node in the tree, you look at the height of its left subtree and the height of its right subtree. The absolute difference between those 2 heights can be no more than 1.
No more than 1 difference everywhere in the tree.
Everywhere. This property prevents the tree from becoming excessively lopsided one way or the other.
Lopsided, like leading towards the extremes.
Exactly. Which brings us to that spectrum shown in figure 7-8. On one end, you have the ideal case, like that perfect binary tree. Maximum branching, fully realizing the divide and conquer benefit. Super efficient.
And the other end?
The other end is the worst case, the degenerate binary tree. This is where it gets so unbalanced, so lopsided that basically every node only has 1 child, maybe all left children, or all right children.
So it just looks like a line.
It essentially becomes a linked list. All the branching potential is gone.
Wow. Okay, so structure really matters.
Hugely. And the source gives us table 711 to quantify just how much it matters, comparing that best perfect structure to the worst degenerate linked list structure.
Let's see some numbers.
Okay, consider the number of nodes at some level I. In a perfect tree, it's exponential, 2i1. In the linked list version, it's just 1,
Big difference.
Huge. Number of leaf nodes for a given height, h. It's 2s in the perfect tree, just 1 in the linked list. Total nodes for height, h. Again, exponential for perfect, 2x plus 1, but only linear h plus 1 for the linked list.
Okay, so the perfect tree packs way more nodes into the same height.
Exactly.
Okay.
Or look at it the other way. For a fixed number of nodes, say n, what's the height? For a perfect tree, the height is logarithmic relative to n, roughly log base 2 of n plus 1 minus 1. It grows really slowly. But if for the degenerate linked list with n nodes, the height is basically n1. It grows linearly.
Wow. So log n height versus n height.
And that translates directly to performance. Think about searching. In that linked list case, you might have to check almost every node. That's linear time order of n, O(n).
Right.
But in a balanced, perfect-ish tree, because the height is logarithmic, searching often takes logarithmic time, O log n, which is vastly, vastly faster, especially when n gets large. The shape isn't just aesthetics. It dictates efficiency.
Okay, wow. So let's recap. We've really dug into what a binary tree is, this nonlinear node and pointer structure. We've got the vocabulary down: root, leaf, edge, level, degree, height, depth, remembering that edge versus node counting thing.
Right. Crucial distinction.
We saw how they're built by connecting nodes, but also how simple insertions removals can impact the whole structure, sometimes needing more complex operations.
Maintaining shape.
And we looked at those key shapes: perfect, complete, full, and balanced, and saw the stark contrast between the super efficient balance forms and the degenerate linked list form, quantified by things like height and node counts.
Yeah, I think the bottom line is binary trees. Super powerful for hierarchy and divide and conquer. But their actual structure, how balanced they are, makes a night and day difference to how well they perform. Understanding these shapes is just fundamental to using them effectively.
Absolutely. Well, this journey through the Hello Algo material has been pretty thorough. Hopefully, breaking it down, like the what, the why, the different forms, helps make this really foundational data structure feel a bit more solid for you.
Definitely. And maybe, as you think about this later, try sketching some out. Draw a perfect one, then a complete one, then make one really skewed. See how those pointers connect and how the overall height changes.
Yeah,
It helps solidify it.
good idea.
And, that leads to maybe one final thing to chew on. If we know that keeping the tree balanced, avoiding that degenerate linked list shape is so critical for performance,
Yeah.
what kind of extra work might be needed? When you insert or delete a node, how could you automatically maybe rearrange things just enough to keep that balance to preserve that logarithmic efficiency, even as the tree grows and shrinks?
So not just adding or removing, but actively managing the shape.
Exactly. Something to ponder.
Definitely food for thought. All right, that wraps up this deep dive.